Welcome to Lesson 70 of Pre-Algebra, and this is direct variation problems. So if you'll recall in Lesson 69, we discussed direct variation, and what direct variation has, specifically two characteristics. And those two characteristics of direct variation are when one variable is equal to 0, the other variable must be equal to 0 as well. And when we saw this on a graph, it was at the origin, or 0, 0. When one variable changes, the other variable must change by a constant factor. Or when we're talking something like a graph, we're talking about m, or the slope. Now, both of these characteristics means that problems that deal with direct variation are proportional, which we use k to represent. In our book on page 473, we have an example of the number of CDs sold and how much the CD was sold for. So as you can see right here, we had one CD and it sold for $15. Two CDs sold for $30, three sold for $45, and four for $60. So let's take a look at this and see if this actually is proportional. So if we take 15 divided by 1, we get 15. If we take 30 divided by 2, we get 15. 45 divided by 3, we get 15. And 60 divided by 4 is 15. So this part right here meets one of the characteristics, and that would be characteristic number 2. The other thing we want to check is to see if when one variable is equal to 0, the other variable will be equal to 0 as well. So if we sell 0 CDs, we're going to make 0 money. So this is check for characteristic number 1. So this is proportional. Now we looked right here and we figured out that 15 is our constant, or our k, because it is constant between each one of these different scenarios. We have the 1 and 15, the 2 and 30, the 3 and 45, the 4 and 60. So with that, if we were to ask, how much would it cost to purchase 6 CDs? Well, we would say, well, we know that each CD sells for $15, and that's our constant. And if we multiply that by 6, we're going to get $90. And that's how the direct variation relates to word problems. So if we continue on down to example 1, which you can follow along on page 471 in your book, it reads, the amount Ellen charges for banquet food varies directly as the number of people that attend. If Ellen charges $780 for 60 people, how much does she charge for 100 people? So we can look at this and we can see that $780 for 60 people, we can kind of come up with something that we've called a unit rate before. If we take 780 and we divide it by 60, which this reduces down to $13 per one person. Now, with this new rate that we've got here, we could get the price for any number of guests. And in this case, the problem is asking us for 100 guests. So we can say, well, 13 times 100 is $1,300. So Ellen is going to be charging her client $1,300. Now, this should seem very, very familiar to us. We've done something very, very similar to this before, and we can do it in what's called a ratio or proportions. So we can say 780 over 60 is some cost, which we're going to label as X, over 100. Because 60 goes with 100 because that's the number of guests, and 780 is going to go with whatever this X is because it's the money. So we would cross multiply, which looks like this. So what's in the same line gets multiplied together, so we'd have 60x equals 780 times 100. Now let's divide by 60 on both sides, and we want to divide by 60 to get x by itself. And the way we get x by itself is 60 divided by 60 is 1, and 1 times x is just x. And then over here, well, we know that 60 goes into 780 13 times, and 13 times 100 is 1,300. So we get the same answer, we just use a different method to find it. And both methods are acceptable, and sometimes it's easier to use solving for a constant and then solving the information, and sometimes it's just easier to do a proportion or a ratio. Okay, now we're going to talk about example 2, which is on page 472 of your book. And it reads, driving at a constant speed, the distance Maggie travels varies directly with the amount of time she drives. If Maggie drives 75 miles in 1.5 hours, how long does it take her to drive 100 miles? So it says in the problem that she drove 75 miles in 1.5 hours. Now this is a constant, or our k. If we divide that down here, we can say that 1.5 goes into 75. We move the decimal place over 1 to the right, and what you do right there, you must do right here. We fill that in with a 0, and we start dividing. So 15 goes into 75 5 times. We subtract that, and it's 75, and we get 0. So here we can say that it's 50 miles per 1 hour. Okay, so from very early on in our book, we remember that rate times time equals distance. Now we have our constant, or a rate, at 50 miles per 1 hour. They're asking us how long would it take for her to drive 100 miles. So they're asking us for a time because they said how long. And so we're going to just leave t right here, and we're going to set this equal to 100 miles because the distance that they told us they wanted us to find was 100 miles. So in order to get t by itself, what we're going to do is we're going to multiply by the reciprocal, which is 1 over 50. Now, why would we choose to multiply by 1 over 50? Well, we would choose to do that because 50 divided by 50 is 1, and 1 times t is t. So these cancel out, leaving us with just t on the left side of the equation. And then, well, don't forget, what you do to one side, you must do to the other. So we still need to multiply by 1 over 50 here. And then 100 times 1 is 100, divided by 50 is 2. So it takes her 2 hours to drive 100 miles. Okay, so we're going to move on to example 3, which is on page 472 of your book. Example 3 reads, there were 23 people in line in front of Delia waiting to be helped. 3 minutes later, there were 18 people waiting in front of Delia. Predict how much longer Delia will have to wait to be helped. Well, so she's standing in line, and there are 23 people in front of her. Kind of sounds like you're at the DMV. 3 minutes went by, and now there are 18 people in front of her, which means that in that 3 minutes, 5 people were helped. So we can come up with kind of a constant here, or a ratio, and we can say, well, every 3 minutes, 5 people were helped. Okay, and then this, when we put it into a decimal form, is 0.6 minutes per person. Now, this doesn't account for every scenario because it's unlikely, like highly unlikely, that there would only be a little over half a minute for every person in line in front of you. But it can give us an estimate of how long she has to wait. So we know that there are 18 people still in front of her, and at 0.6 times 18, we can figure out about how long she has to wait. So we'll come over here, we'll do 18 times 0.6, and we'll do 6 times 8, and we get 48. 6 times 1 plus 4, and that's 10. And then all we have to do is move the decimal place over, and we'll come over here and do the same. So we're looking at 10.8 minutes. Now again, we're looking for an estimation. So we're talking about 11 minutes left for her to wait.